Hello, class. Another good example for centripetal force is gravitation, which forces satellites to move in a circular path around the Earth. But before we jump there, let's examine where the definition of gravitation came from. If the force of gravity is being exerted on objects on Earth, what is the origin of that force? Newton's realization was that force must come from Earth. He further realized that this force must be what keeps the moon in its orbit. The gravitational force on you is 1/2 of the third law of pair. The Earth exerts a downward force on you, and you exert an upward force on the Earth. When there is such a disparity in masses, the reaction force is undetectable. But for our bodies, more equal in mass, it can be significant. The gravitational force exerted on the moon by the Earth, and here's an example of the gravitational force exerted on the Earth by the moon. Therefore, the gravitational force must be proportional to both masses. By observing planetary orbits, Newton also concluded that the gravitational force must decrease as the inverse of the square of the distance between the masses. So in layman terms, any object with a mass attracts each other. Well, all objects have masses, so all objects are attracted to each other. Now, if you take your pen and paper next to each other, they feel a gravitational pull. However, it's so small that you won't notice its effect. However, if you take your pen as an object 1, and let's say the Earth as object 2, you'll notice the gravitational effect of the pen wanting to come closer to the Earth. And if you let go of the pen will fall towards the Earth. To calculate the numerical value for gravitational force, we have f of g equals big G times m1 times m2 all over r squared. The big G is a gravitational constant, and that value stays the same value of 6.67 times 10 to the negative 11. M1 is the mass of object 1, and M2 is the mass of object 2. Now R is the distance between the center of both objects. It's important to remember that it's the center of both objects because one of your objects could be as big as the Earth. And there's a big difference between the center of the Earth and the surface. Alright, here's our first example. We have a 50 kilogram person and a 70 kilogram person sitting on a bench close to each other. Estimate the magnitude of the gravitational force exerted on each other. We'll say they're about 0.5 meters distance between each other. We just apply our new gravitational force equation. And then plug and chug, and we get a value of 1 times 10 to the negative 6 newtons. This is so small that you won't notice its effect. Alright, next example. What is the force of gravity acting on a 200 kilogram spacecraft when it orbits 2 Earth radii from the Earth's center? That is, the Earth's radius is 6,380 kilometers above the Earth's surface. The mass of the Earth is 5.98 times 10 to the 24th kilogram. Again, we'll start with our new equation. Just plug and chug, and we get 4,900 newtons. Whoa, that's a big number. The spacecraft is actually falling around the Earth because the altitude is so high it will never hit the ground. So literally, the spacecraft is falling around the Earth. Now, we've used F of G for weight and for gravitational force. Well, guess what? Weight equals gravitational force. Let's take a look at an example of an object's weight close to the surface of the Earth. So M is object 1, and the mass of the Earth will be object 2. The distance between these objects is roughly the Earth's radius. If we set both equations equal to each other, the mass of object 1 will cancel out, and we're just left with G equals big G times the mass of the Earth all over the radius of the Earth squared. Now, if you were to plug and chug the actual value for the mass of the Earth and the radius of the Earth in that equation, guess what your answer will be? That's right. It will be 9.8 meters per second squared, the acceleration of gravity. This equation is important to remember because we can also use the same equation to calculate the acceleration of gravity on the moon just by plugging in the mass and the radius of the moon. And with the acceleration of gravity on the moon, we could technically calculate the weight of an object on the moon, which would be different than on Earth. Okay, let's redo this example with our new knowledge. First step is to write down the gravitational force equation. We see that r is 2 Earth radii away. And we'll set the mass 1 to the mass of the Earth and mass 2 to the spacecraft. Let's factor in that squared so that we get 4 times re squared. Do you notice where we could simplify this equation? That's right. If you recall, the acceleration of gravity equals capital G times the mass of the Earth all over the radius of the Earth squared. So let's make that substitution, and the equation reduces down a bit. Now we do an easy plug and chug to get 4,900 newtons. Here are some examples of what values for acceleration of gravity equals at different location and height. Because the Earth is not perfectly spherical, the distance between the center of the Earth and an object varies slightly according to location. Also, the altitude starts to affect the acceleration of gravity if it's really high, because the object is now that much further away from the center of the Earth. Let's take a look at this example. We want to estimate the effects of the value of G on top of Mount Everest, which is 8,850 meters above sea level. That is, what is the acceleration due to gravity of objects that are allowed to fall freely at this altitude? Using our new equation, all we have to do is plug and chug, and we get 9.77 meters per second squared as acceleration of gravity on top of Mount Everest. So it's slightly smaller than our 9.8, which is close to the surface of the Earth. Alright, here's an example of a satellite falling around the Earth. If it's at a high enough altitude, depending on the altitude and speed, the orbit could change from circular to elliptical orbit. Falling around the Earth is the weightless feeling that you feel in space. Okay, next example. A geosynchronous satellite is one that stays above the same point on Earth, which is possible only if it's above a point on the equator. So for part A, we want to determine the height above the Earth's surface such that a satellite must orbit, and then part B will calculate the speed. The satellite is moving in a circular path. So we'll start with sum of the forces in the radial direction equals MAC. Our centripetal force causing the satellite to move in a circular path is gravitation. And we'll also make the substitution in for centripetal acceleration. Look at all the things that cancel out. However, we don't know what speed is. But again, we can use 2 pi r over t. Our period for one revolution on Earth is 1 day, or 24 hours, which in seconds is 86,400 seconds. Since we're solving for r, we need to make that substitution into our equation. And then we start solving for r. Oh, first I factor in the square, and then I start solving for r. And we get our final equation. Then all we have to do is plug and chug to get 4.22 times 10 to the 7th meter. Or I can just say 42,200 kilometers. But this value represents the distance between the satellite and the center of the Earth. The question asks for the distance between the surface of the Earth and the satellite. So all we have to do is subtract the radius of the Earth to get an altitude of about 36,000 kilometers as the satellite's altitude. Now for part B, we need to find the speed of the satellite. Again, we'll start with sum of the forces in the radial direction equals MAC. And again, we'll make the substitution of gravitational force and centripetal acceleration. A lot of things cancel out, and we're left with a very reduced equation. It is just one algebra step to solve for speed. Plug and chug, and the speed of the satellite orbiting the Earth is 3,070.